All right, folks, it's Bass Action back in action here. In this video, we are going to look at all the basics of polynomial functions, just a really quick summary of what you did in your Algebra 2 days. And here at the beginning, we are going to just take a small little spin and twist on something you did in your Algebra 2 days. So let's start with that. Looking at end behavior. Okay, so the end behavior of our polynomials, thinking back to your Algebra 2 days, was based on the degree of the polynomial, okay? So it was based on that highest exponent that you would see. And if that highest exponent was odd and the leading coefficient was positive, back in your Algebra 2 days, you would just give these little arrows here for what the ends of the polynomial would look like. So if it was odd and positive, you drew these little arrows. If it was odd and negative, you drew these arrows. If it was even and positive, you did these, and even and negative, it was these. Now, depending on your Algebra 2 teachers, what they may have pointed out to you is that you knew these end behaviors because odd degree polynomials behaved like lines. So if it was odd and positive, it behaved like a positive sloping line or negative sloping line. And when it was even, it behaved like, the ends behaved like a parabola. So if it was even and positive, it behaved like this upward turning parabola, and even and negative, it behaved like a downward turning parabola. And what they may or may not, again, have filled in for you is that in the middle, the polynomial could look like any variety of thing. Okay, if it was even and negative, again, it could look like any negative thing. We could fill all these in for our positives. Our negatives could look something like this. Now, we still need to know that end behavior, but what we do need to understand now is how to write this in terms of our new limit notation. And in terms of our new limit notation, what we're going to do, let's break that language down again. The limit of f of x, meaning what is happening to these y values, as our x values are going towards negative infinity. So on this figure here, as our x values go to negative infinity, we can see, in fact, the y values are also going to negative infinity. And just looking at our little figure, as the x values go to positive infinity, it's also going to positive infinity. On our next one, that of course is going to flip. As we go to negative infinity, now we're going to go up. So positive infinity, and as we go to positive infinity, we're now going to go down. So those just reverse, okay? On our even degrees, again, breaking down our notation, what's happening to the y values as we go out here towards negative infinity, the y values are going up. Now, of course, it's going up for both. So both of these are going to be positive infinity. And when that leading coefficient flips, it now just becomes a negative infinity for both. So until you get really comfortable with this limit notation, I strongly encourage you to still draw these ends just like you would have done in your Algebra 2 days. No big deal to draw those, because then it's really easy to see how to write this new notation. Now, the next thing that we do want to summarize, and we're going to do one example on this page together, is just all of these big ideas that you would have done, probably lots of discovery activities in your Algebra 2 days, understanding these. Okay, zeros, roots, and solutions for a polynomial. All these words mean the same thing. So if it asks for the zeros, the roots, or the solutions, it's asking always for the same thing. You will factor wherever it was possible, or you're going to use some hints. And we're going to do practice with all of these, but I just wanted you to have a good summary. We will also revisit this idea of the P's and Q's later. And then we're going to learn something new here called the intermediate value theorem. And I'm just going to give you the spoiler right now. We're going to look for sign changes. But don't worry about this piece right now, because it's for a lesson later down the road. We're just trying to get a good summary. Remember that the total number of solutions for the polynomial should always equal whatever the degree of the polynomial was. Zeros, roots, and solutions, we also should have learned that they can be both real numbers or imaginary numbers, okay? So solutions, roots, and zeros can be real or imaginary. Now, x-intercepts, zeros, roots, and solutions can also be called x-intercepts, but only when those are real, okay? So our zeros, roots, and solutions is going to match our degree. some of them will be real numbers, and those real numbers will become x-intercepts. Imaginary numbers, we should always remember, will be coming in pairs, and those are called complex conjugates. Again, we will be reviewing all of this, but it's good to get a nice summary and just remember, you know these things, okay? So complex conjugates. Next is, you guys would have talked about multiplicity, and that's just the repetition of a zero. So it's how many times a zero is repeated. So if a zero has an odd multiplicity, I mean it's repeated an odd number of times, it is going to cross through the x-axis. We're going to look at an example here with this in just a moment. If the zero has an even multiplicity, then it is going to do that little touch and turn, that bounce, okay? So depending who you had, they might have phrased it differently. So touch and turn, okay? Our end behavior, that's going to be based on what's up above. Our our y-intercept, always remember that means to let x equal 0. And the graph cannot have more than the n minus 1, where n is that degree, okay? So the number of turns is going to be our degree minus 1. Now, it might not turn that many times, but that's going to be our max. And the last thing they may or may not have told you is that graphs of polynomials need to be smooth. So they shouldn't look pokey, is how I always tell my students. Smooth and continuous. There will never be any breaks in these. This, of course, is different than our rational functions that do consistently have breaks in those polynomial or in those graphs. Now, let's just take a quick look at a graph and how we can take all this information in this beautifully factored form and put all of this together. Okay, so we're just going to make ourselves a quick little graph using all of our concepts here. So the first thing we would do, since they've given it to us in factored form, and you'll notice the next one is not factored, we're going to do that one together later. But let's look at how we can apply these ideas to an already factored one. First of all, we can find our degree by adding up all of our exponents. So I have 2. This only has a 1 here, so 2 plus 1 plus another 2. So our degree on this polynomial is going to be 5. Okay, so we're going to have our degree is 5. Okay, which means the maximum number of turns we'll have will be 4. Okay, so our degree is 5, and our coefficient is positive. Our leading coefficient is going to be positive. So we have our degree is 5, positive leading coefficient. Our ends should look like a positive sloping line. So I always like to give myself some nice little arrows here to remind me that that's what that should look like. That also means that we can go ahead and we could right now write that limit notation. So we could say the limit of our function as our x goes to negative infinity is going to be negative infinity. And the limit of our function, so what's happening to the y values, as our x values go to positive infinity is going to be positive infinity. My negative did not show up very nicely there. So once we know that end behavior, we can actually write that immediately. The next thing that we can do is we can actually identify all of our zeros. So we're going to have a 0 here at 0, and it's important to notice that this one is a double. So we're going to have a touch and turn there. So let's put our 0 on here and know we're going to have a touch and turn. We're going to have a 0 here at x equals a negative 3, but that's just a single, so it's going to cross right through. So I'm going to go ahead and put that here and go ahead and write in my negative 3. And I'm going to have a 0 here at 1, and that one's also a double. And that's also then going to be a touch and turn. Notice I'm not trying to even make this to scale. I'm just trying to put those zeros in the proper places and just kind of in order. We would also want to find the y-intercept. And again, we would, of course, find our y-intercept by letting our x equal 0. But if we know that the graph is crossing at 0, 0, then we also have the y-intercept without doing really any math there. Okay, so now let's just put this together quickly into a graph. So I know that from my ends, these are supposed to be going. From my outermost intercepts, they're supposed to follow that end behavior. From here, I'm going to follow my other information. This 1 is supposed to be a double. So this 0 here isn't supposed to go through. It's supposed to make this nice little touch and turn here. This 0 here is also supposed to be a little touch and turn. So somewhere here it's going to turn. I don't know where, and I don't worry about trying to find how high it should go. That does not matter. We're going to leave that to your calculus classes. So then here is my other little touch and turn. And I'm going to somewhere just make it turn and come down so it'll turn eventually and go through my other intercept. Now, this is a decent enough graph for us. You could type this into Desmos and see exactly what it looks like, but I really want to emphasize what matters to us is smooth and continuous. Our maximum number of turns did match, okay? Our end behavior was correct and our intercepts were correct, and that's really all that matters for us.